another level of structure. So that was secondary. The third one is tertiary, third degree structure. Okay. And that's the fully folded shape. And that's determined by interactions between side chains. So between different side chains. And that is, and mostly, there are some exceptions. And all proteins have these three. You can look at any protein from the point of view of primary structure, secondary structure, or tertiary structure. And tertiary structure is where we're really going to get into the stuff that we want to talk about more now. We can explain more and the kind of things that we've been playing with. So I want to switch back in a second. If you look now at it would be page 7 of today's information packed handout. It's got the pictures for tertiary structure. So let's take a look. So here we go. Here's the story. This is beta globin. Again, I'll put the spin back on. That coily stuff is the backbone. So the spirals are done by hydrogen bonds. What tucks it in like that? What keeps it compact? We talked a little bit about that on Monday, amino acid side chains interacting. So I want to give you a for instance. Do you see that green part and that red part? They're actually fairly far apart if you stretch the protein out. But they're close together in the folded protein. Why? Because of an ionic bond between the two of them. So if I turn the spin off, I can zoom in. And what you see, it takes a minute to push this around until you get the right way. There you go. What you see is here's the green part, and there's the red part. And again, normally, they're quite far apart if the protein was stretched out. But this is a histidine side chain. And that nitrogen, it turns out, is positively charged. And that is a aspartic acid side chain. And that side chain has a negative charge. And so that plus and minus attract each other, and they pull the protein in. And that's not all that holds the protein in shape, but one of many things that sort of staple the protein into a shape. These are one of many non-covalent interactions that pull the protein into that shape. Questions about what you're seeing here and what that means that ionic bond holds that shape there. All right. What I want to do, if you look on today's, like I said, handout, it'll say, let's see, do this carefully. If you, what I'd like to do is have, I'm going to switch off from this and back over to here. So what we had here was ASP 94 had a minus charge, and it was ionic bonding to this side chain of His 146. What do the numbers mean? Number in the sequence. First amino acid, leucine 1, then there's something other 2, 3, 4, 5. So it doesn't mean the 94th aspartic acid, it means amino acid number 94 is aspartic acid. Histidine 146, that's the very last amino acid in the chain. Okay? So my question to you, and this is a thing to talk to your neighbor about, if you on page, so Biochem 6-11 has amino acid structures. What I want to know is another amino acid that could substitute for His 146. So basically, suppose you wanted to engineer this protein and to do an alternative form, your own particular personal version of hemoglobin, right? I want to make that ionic bond form. Must that one be histidine to make an ionic bond, or are there other amino acids that might also work to make that ionic bond with aspartate 94? So think about it, talk to your neighbor. Can you find another amino acid whose side chain could make an ionic bond with asp 94, or might possibly swap for his 146? So think about it, talk to your neighbor, and we'll pick names in a sec. Let me